Hey, welcome back to HackCodeNet. Today we're going deep on JSON web tokens, how they actually work under the hood, and the handful of mistakes that let attackers forge them in the real world. Let's get into it. Here's the basic idea. A client logs in once, and instead of the server remembering a session, it hands back a signed token at JWT. On every future request, that token rides along and proves who you are, without the server needing to look anything up. That statelessness is what makes JWTs so popular for APIs. It's also exactly why a broken implementation is so dangerous. The token itself is the entire trust boundary. Structurally, a JWT is just three base 64 URL encoded chunks joined by dots, a header, a payload, and a signature. There's no encryption here by default. If you grab any token and decode the first two segments, you'll read them in plain text instantly. That's intentional. The security isn't supposed to come from hiding the contents, it's supposed to come entirely from that final signature, which proves nothing was tampered with after the server issued it. The header is a small JSON object declaring the token type and, critically, the signing algorithm in the alg field, things like HS256 for a shared secret, or RS256 for a public-private key pair. This tells the server exactly how to check the signature. And that turns out to be one of the most dangerous fields in the whole token, because in a lot of implementations, the client effectively gets a vote in how its own token gets verified. The payload holds the claims, user ID, role, expiration, whatever the application wants to attach. Here's the part that trips people up. Anyone can decode this and edit it in seconds with zero special tools. Flipping role, user to role, admin takes about as long as it takes to say it. The payload was never meant to be secret or tamper resistant on its own. All of that protection has to come from the signature. The signature is computed by running the header and payload through a signing algorithm using a secret or private key. Its only job is answering one question: could this token only have come from someone holding the correct key? If the server checks that correctly, the payload can't be quietly edited. If it checks that incorrectly, and you'd be surprised how often that happens, everything else in the token becomes a suggestion, not a guarantee. Classic session-based auth keeps a record server-side as session ID maps to a user in a database, and it can be revoked instantly. JWT auth flips that. The server signs a token and then forgets about it, trusting the signature on every future request instead. Great for scaling across many servers with no shared session store. The catch is there's usually no built-in way to revoke a token early. If it's signed and unexpired, it gets in full stop. The spec actually defines an algorithm value called none, meaning an intentionally unsigned token. Some server libraries implemented this carelessly. If the header says none, they'd skip signature verification entirely and just trust whatever the payload says. So an attacker decodes a real token, edits the payload to whatever they want, sets ALG to none, strips the signature segment, and re-encodes it. If the server doesn't explicitly check which algorithms it's willing to accept, that forged token walks right through the front door. HMAC signed tokens are only as strong as the secret behind them. If a developer signs tokens with something short or guessable, a word, a company name, something copy-pasted from a tutorial, an attacker can capture a single token and throw it at an offline cracking tool. HMAC verification is fast, so tools built for this can test billions of candidate secrets a second against a word list. Once the secret's found, the attacker can sign whatever payload they want, no interaction with the server required. This one's subtle. Some systems use RS256, where the server signs with a private key and verifies with a public key, a key that's often shared openly, sometimes even published at a URL. If the verification code doesn't strictly pin down which algorithm family it expects, an attacker can take that public key value, sign a forged token using HS256 with it as the HMAC secret, and send it in. The server verifies using HMAC with the exact same public key value, and of course it matches, because the attacker used it to sign in the first place. Some implementations support a JWT header, letting a token embed its own public key directly for verification. Read that twice. If the server accepts a self-declared key without checking it against a trusted list, an attacker just generates their own key pair, signs a forged token with their private key, and staples their matching public key right onto the header. The server verifies using the attacker's own key and, unsurprisingly, everything checks out. Closely related is the JWT header, which points to a URL where the server fetches a key set to verify the token. If that URL isn't restricted to a trusted allow list, an attacker hosts their own key set on infrastructure they control, points CHQ at it, and signs with the matching private key. The server fetches keys from an attacker-controlled address and trusts them completely same result as the JWT attack, full token forgery. Every one of these bugs comes from the same root cause, trusting attacker-controlled data during verification instead of fixed, server-side configuration. So the fixes are consistent. Hardcode the algorithms you'll accept and reject everything else. Use long, truly random secrets, or asymmetric keys with proper rotation. Only trust keys from your own configuration, never from a value or URL embedded in the token. Keep expiry short, and pair JWTs with a lightweight revocation list if you need real logout. Security here isn't about a fancier algorithm, it's about never letting the token decide how it gets checked. That's JWT security in a nutshell. If this helped things click, smash that like button, hit subscribe for daily hacking, coding, and networking content, and I'll catch you in the next one. Thank you so much for watching.